love cherry Pepsi. What is in this anyway? Lots of sugar, some phosphoric acid, and lots of caffeine. 63 milligrams of caffeine in this bottle. Hey, I know. I could have students figure out how many molecules of caffeine are in 63 milligrams. That'd be a good idea. So if you can figure that out, that'd be extra credit for next class. Make sure you show all your work, however. Gosh, I wonder what a molecule of caffeine looks like if I only knew.
This is a molecule, caffeine. You all know caffeine is in coffee and caffeinated soda pop. And you can kind of see here what that molecule looks like. The molecule has carbons, hydrogens, nitrogens, oxygens. And you can see here, there are the nitrogens, here are the carbons, here are the hydrogens. Carbons are the gray ones, and the oxygens are here. These are double bonds to them. And just kind of a cool drawing of the molecule. Obviously the atoms are actually closer than this, and you can see that in a what's called a space filling of those molecules. Those atoms. Those atoms get a lot closer than they were before. So that is caffeine. Now caffeine has a molecular formula of C8H10N4O2, and I'm going to show you why that is important. Alright, so you get to see caffeine move there, but here are some pictures of the molecules with the letters on them, and that's about it. So you can see here we have our carbons and nitrogens and hydrogens and oxygens. Here's the molecular formula, C8H10N4O2. And this is another form that is often written with, or shown with organic molecules, where the carbons are just, it's called the line angle formula, where this is where a carbon is. A carbon is at each corner, there's carbons. So the empirical formula would be half the molecular formula. So when we're figuring out molecular formula problems, there's always the molecular formula is always a multiple of the empirical formula. In this case, the multiple would be 2. So what is a molecular formula? It is a formula that gives the actual number of atoms of each element in a molecule. So it's the multiple of an empirical formula. So the example I just showed you, for caffeine, the multiple is 2. Well, is that always the case? No, it's not. It depends on what you have. For instance, what if it's glucose? Let's take a look at that now. This is a molecule of glucose. Glucose has a molecular formula of C6H12O6. So that's what the molecule looks like, C6H12O6. That'd be the molecular formula. Since it's C6H12O6, the empirical formula would be the lowest whole number ratio, which would be CH2O. So again, reason why we talk about the difference between a molecular and empirical formula is because this is what the actual molecule looks like. It's not CH2O, it's C6H12O6. But there is a lowest whole number ratio of elements, and if we separated the elements, that'd be what the percentages would be. We'd be able to find the mass percentage of each element, and then that would tell us the, also we could be able to figure out the lowest whole number mole ratio, which is our empirical formula. But for this molecule of glucose, molecular formula C6H12O6. So that was a picture of glucose. So again, here is what glucose looks like. It is a molecular formula of C6H12O6. And whoops, that should be a little smaller, right? An empirical formula would be the whole number ratio, CH2O. If you're talking about water, the molecular formula is H2O, and its empirical formula is H2O. So it is possible that you can have both be the same. So the multiple in that case would just be 1. The multiple here would be 6. So the molecular formula is always a whole number multiple of the empirical formula because it depends on what you have for a molecule. But it's always a certain amount of whole numbers of the empirical formula. So let's take a look at some problems and how that would look to you. So you are given the empirical formula in this case, CH2O. You are given the, that's the one we just talked about. That was the empirical formula of glucose. So let's see if we're talking about glucose here. So molecular formula for a compound has a molar mass of 120.12 grams per mole. So how are we going to do this? Well, we're going to have to take the molecular formula mass divided by the empirical formula mass, and that will show us how many multiples there are. So that equals the multiple. And I'll show you what I mean by that. So I'm going to take the mass that says here, 120.12 grams per mole, and I'm going to divide it by the mass of the empirical formula. So 12.01 grams for the carbon, 1.01 grams for each hydrogen, and 16.00 grams for the oxygen. If I add all that up together, I get 30.03 grams per mole. It doesn't really matter what unit I use here. It could be AMUs if we're just using formula mass, but if it's grams per mole, I divide that and I get 4. That's my multiple. So I take 4 times my empirical formula. That's what I mean by a multiple. So my actual molecular formula, C4H8O4. Alright, so that's one example of a molecular formula. Let's do another one. In this case, we are not given an empirical formula. We are given masses like we were with when we did empirical formulas. So if that is what is happening, you are going to have to change the grams to moles and figure out the empirical formula first. So some cases they're given to you, some cases they're not. So I'm going to do a little bit of math here to figure out these moles. I don't have them memorized. So if I take them, 4.04, I get 0.2883, just more numbers, moles of nitrogen. And if I do the oxygen, I'm going to get 0.716 and 25. That's all the numbers, so I'm just going to use them. So remember, empirical formulas are going to divide by the lowest whole number ratio, or lowest number. I get a 1-to-1 here. Divide by the lowest number here. Again, I get about approximately 2.5-to-1. As you remember last time, with the empirical formulas, if we do that, we have to multiply by something to get us whole numbers, and if we do that, we'll get a 2-to-5 ratio. So we have an empirical formula of N2O5. So now we're back to the beginning of last problem. We have an empirical formula, and we have a molar mass of the whole molecule. So we are going to take the mass of the whole molecule, which is 108.0 AMUs, or it's the formula mass, which same number. Then we take the formula mass of the empirical formula, so it's 2 times 14.01 AMUs. Remember, it's the same number as the molar mass, plus 5 times 16.00 AMUs. When we add all those up, we get 108.02 AMUs. Well, that looks a lot like this. So my multiple is going to be 1 in this case. In other words, my empirical formula was N2O5, and my molecular formula in this case is also N2O5. So that can happen. It doesn't happen every time. It did with water with the other example. With the glucose, the multiple was 6. With the caffeine, the multiple was 2. Look at one more. This one is beta-carotene. It's a big molecule. And we've looked at 2 of them already. We are now giving you the molar mass, 536 grams. And here's the empirical formula, C5H7. And this is a good one for you to try. So bring this to next class. Bye-bye.